Okay, yeah, good. All right, we're going to talk about phase now. Phase will be incredibly important in the next chapter. The next chapter will talk about how waves interfere, and it's all about phase. So this is crucial. Okay, so here's this is the equation for the displacement of a transverse wave, right? Okay, now phase. What's phase? I can use that thing. This is called the phase. It's just an argument of the sign. All right, that's all. Well, it's important. So if we feel like it, we can write this. Now look it. We're not doing this to just be lazy. There's a reason, and you'll see it next chapter, all right? But anyway, that's the phase. Now, don't forget, what's so special about sine and cosine? Periodic in 2 pi, right? So it looks the same. Every 2 pi, it looks the same. So if you have sine of x, you get some sine wave. If you have the sine of x plus 2 pi, you get the same thing. Sine of x plus 4 pi, same thing. It's periodic in 2 pi. So here is a 2-dimensional wave. So that's the thing, like you have some water in a pot or aquarium or something. You drop a little pebble. You're looking straight down. You have no depth perception. So here's the source. And so you see these circular waves moving out. All right. Now here's another term for you. Sorry. Wave front. What's a wave front? It's the max. It's the crest. So, for a 1-dimensional wave on a string, we have something like that, right? So you'd call this the crest. I call it the max. The crest or the max. Okay. For a 2-dimensional wave, they call it a wave front. Whatever. Okay? All right. So wave fronts are the crests of the wave. And of course, come on. What's the distance between here and here? It's a wavelength. So what's the distance from one wavefront to another? It's a wavelength, right? So there's a wavelength, there's a wavelength, there's a wavelength. Okay, no kidding. All right, so the circular wavefronts move outward from the source at speed v. So the source, let's just say that, I don't know, let's say again we have just a little bit of water in an aquarium, just a little bit of water, and we have like a little hammer or something that moves up and down. So that would be the source, right? That would create those 2-dimensional waves. Okay? Now, remember, we're talking about phase. So phase is the argument of the sign. So we have the displacement equals a sine kx minus omega t plus phi 0. And this thing here is the phase. Okay, so here's the question for you. Here's the question. Just consider the phase, the argument of the sign. What's true about the phase here, 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 and here? What's true about the phase? Well, it's the same, right? It's the same. Or it differs by 2 pi. Agree? Because you get the max, right? So it's the same or it differs by 2 pi. Because sine is periodic in 2 pi. Okay, that makes sense, right? It makes sense. All right. Okay, now what we want to do, though, we want to get a bit more complicated. Okay, so the last question was simple, right? Because we just said, what's true about the phase from here to here, between here and here, and here and here, and here and here, or here and here and here. Well, it doesn't, whatever, It's always same or factors of 2 pi because it's the max. But now what we want to do is we want to generalize. So now we want to pick any 2 points on the wave. I don't care, any 2 points. So pick here, whatever, who cares, any 2 points. And we want to calculate the phase difference, which is what we're going to be doing next chapter, at the same time, all right? The same time, that's the important thing. So what we want to do, we want to calculate delta phi at at the same time. At the same time, right? Okay. All right, no big deal. Okay, so don't forget the phase is kx minus omega t plus phi 0. Don't get these confused. This is a phase constant. That's why it has a little subscript 0 there. This is the phase. This is not the same as that. All right, don't get them confused. All right, here we go. Delta phi, that's what we want. Delta phi. Well, the difference is phi. Let's call this, 1 and 2 or 2 and 1, whatever, right? So we want phi 2 minus phi 1. Okay, I can do that. All right, 2 different positions, right? Same time, 2 different positions. Okay, so that's going to be kx2 minus omega t plus phi 0, right? x2 minus kx1 minus omega t plus phi 0. Right? I mean, it's the same wave, right? It's the same wave, so they have the same phi 0, they have the same omega, same omega, they have the same k, but all I'm saying is we just want to see it's different x, right? Different position, okay? That's why the only things that we need the subscript were the x's. Wow, that's wonderful. Goodbye, goodbye. Goodbye, goodbye. So this is nice. We just have k x2 minus x1. Oh, that's nice. Now, what's k? Remember k, the wave number, 2 pi over lambda? You got to know that. We're going to use it a lot. Sorry. All right. So k is 2 pi over lambda x2 minus x1. All right. And I just feel like writing it a little bit differently. Hope you don't mind. So I'm going to write it as 2 pi. Okay, x2 minus x1 is just delta x. Lambda, I want to put it over here. You'll see why. Okay, so I have the delta phi, which is the phase difference, is that. Now let's just divide both sides by 2 pi. You'll see why. Delta phi over 2 pi equals delta x over lambda. Now, just hold your horses, all right? So that was just algebra, right? But this is incredibly important. Okay, remember, sine is periodic in phase, or period, whatever, and wavelength, right? Right? Okay. So let's see if this makes sense. Okay, let's see if this makes sense. Right there. Okay. So what is delta phi? What's delta? Okay, let's just say that the 2 points were here and here. All right? So, okay? So for those 2 points, what's delta x? What's the position? What's delta x from here to here? A wavelength, right? So delta x would be a wavelength, right? And then what is, according to this equation, so if delta x is a wavelength, this is 1, so what does delta phi have to be? So delta phi has to be 2 pi. No kidding, right? Isn't that what we already said? Doesn't the phase difference from here to here have to be 2 pi? Well, of course it does. Sine is periodic in 2 pi. Okay? All right, so that was one example. Let's do from here to here. Okay, so this was max to max, right? This was max to max. Now let's do min to max or max to min, whatever, I don't care, So now let's do min to max, all right? Okay, now, what's delta x? So for a min to a max or a min to a max, what's delta x? It's a half a wavelength, right? So delta x is a half a wavelength. Well, let's use this formula. Delta x is a half a wavelength. A half a wavelength over a wavelength is a half. So what's delta phi over 2 pi? So delta phi over 2 pi has to be a half. So what's delta phi? Pi, right? Pi. Now, Does that make sense? Well, of course it makes sense. The phase difference from here to here is 2 pi. So what's it going to be from here to here? Pi, right? Okay. All right, let's do, let's do it from here to here, right? So what do you want to call it? 2 maxes? I don't know. So let's do max. All right, so max, and then second max. I don't know. All right? So from here to here. Okay? What's delta x? Well, from here to here is 1 wavelength. From here to here is another wavelength, so it's 2 wavelengths. Okay, so use the equation. So delta phi over 2 pi is delta x, which is 2 lambda, over lambda, which is 2. So therefore, what is delta phi? 4 pi, right? So therefore, delta phi has to be 4 pi. No kidding, right? I mean, from here to here is 2 pi. From here to here is 2 pi. So from here to here is 4 pi. Big deal. So that's all there is to it, okay? That's all there is to it. And this is going to be bread and butter next chapter. We're going to use this all the time. So, I mean, you know, just look at it and think about it. And make sure it makes sense to you, okay? When this moves delta x, this moves delta phi, but this ratio is the same. Delta x over lambda is delta phi over 2 pi. So make sure you understand that. Because it's important, especially next chapter. All right, super important. Put it on your radar screen, I don't know. Put it on your refrigerator. All right, let's, yeah, I just said that. All right, let's do an example. So everybody read it. It's just a review, but it's good. All right. So here you have a nice sine or cosine, who cares, doesn't matter, right? What are the amplitude, frequency, wavelength? Okay, so bingo. What's the, oh yeah, what is this? Okay, notice the horizontal axis is in time. So that means you're seeing one spot of that rope. Let's say it's a rope. You're seeing that one spot that I sprayed with the spray paint. You're seeing that one spot as a function of time. Okay? That's what this means. It's a history graph, right? History graph at x equals 0. So you're seeing what happens at x equals 0. One spot, all right, where it goes. There's a displacement, right? So it starts off at 3, then it goes down here, you know, da, 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 da. Okay, wave traveling to the left at 2 meters per second. Great, all right, whatever. So what's the amplitude? You just look at it, right? The amplitude is this, the distance from here to here. So, bingo, 6. All right, so the amplitude is 6 centimeters. All right, the frequency. The frequency, I don't know. Well, I mean, you know, the unit of frequency is hertz, right? So I don't know what the frequency is, but how do you get it? Frequency is 1 over the period, correct? Okay, so therefore, right? All right, so what's the period? What's the period? Well, you know, from here, stupid graph. All right, from here to here, right? From here to here, 0.6 seconds, right? 0.6 seconds. Or you can just say from, I guess, come on, make it easy. From here to here, right? This is 0.2, this is 0.8, so this is 0.6. So frequency is 1 over 0.6 seconds. What's that? Flip it, right? So therefore, oh, sorry, that was stupid. So there's 1.667 hertz, right? Hertz, remember hertz is a 1 over second, or second to negative 1. All right, awesome. Wavelength. Okay, look at, you can't get to wavelength because this is time. So what are you going to use? We always use when you're confused with waves. F equals ma. So V equals F lambda. Therefore, lambda equals V over F. Velocity is 2 meters per second. We don't care about the direction. Frequency is 1.666 or whatever inverse seconds, right? And so you work that out and you get 1.2 meters. There you go. Let's see. That's a good place to stop.